Okay, so magmas actually boil, which is kind of interesting. Think of a liquid rock boiling. When you heat up water on the stove, you make it go through a phase transition. And when the water boils, you get a lot of steam vapor up on top that comes off of your pan of water that you're boiling on the stove. That is called a phase transition, when the liquid water is converted into gas by raising the temperature of the water that you're heating up on the stove. Well, magmas can also boil, but it's a little bit of a different process. In this case, when the magma is stored deep inside the earth, sort of like this column I've drawn here, where you have H2O, which is water, SO2, which is sulfur dioxide, and CO2, which is carbon dioxide. When this magma column is at high pressure, all of these molecules are dissolved in the liquid. So they're just floating around individually in the liquid. You can't really tell that it's anything more than magma because it's just got all these gas molecules kind of individually swimming around in that liquid. When you release pressure on that magma, you actually force those molecules to form bubbles, gas bubbles. So this is a phase transition where the gas comes out of solution, out of the melt, and forms its own gas bubbles. It forms steam. The steam bubbles have water, sulfur dioxide, and carbon dioxide in them. It's kind of like the analogy of when you open a soda bottle or a soda can after you've shaken it up. When they make the soda and put it into the bottles and cans in the factory, they pressurize it a little bit because the soda has dissolved carbon dioxide in it. And they want to keep that gas dissolved in it because when you open the can and you release the pressure, you basically make the carbon dioxide go into the gas bubbles instead, and that's what makes the soda nice and bubbly. Okay, so this steam pressure that you can build by getting the gas molecules in your magma to start to form bubbles, which then expand, that is what drives explosive eruptions. It's actually what drives every eruption from a volcano because this gas provides the propellant to get that magma out of the magma chamber and conduit to erupt on the surface. So if we take our cutaway cartoon of a volcano here, you see the magma chambers stored way down deep inside the earth. There's a lot of overlying rock that's squeezing down on that magma chamber, making the magma under a lot of pressure. The pipe going to the surface, the conduit, that is where the magma travels up to the surface. And when it does so, the pressure on the magma is released. So you go from very high pressurized magma to magma that doesn't have much pressure on it at all. So way down deep in the earth, I have a cartoon here showing this conduit with these gas bubbles in the magma. Way down deep inside the earth, the gas bubbles are small and there's some gas dissolved in the melt. When the magma starts to travel up towards the surface, it's like you get up to the top of this column. You can see the big blue ovals up there. Those represent gas that's expanding because the pressure is being released. If you think of this as a sealed up pipe, and the gas can't really expand very well, then you're generating big pressures on the top part of the conduit by this expanding gas. So in a volcano, you can have two situations in the conduit. On the left, I have a cartoon. The blue circles and ovals represent the gas that's expanding in the magma as pressure is released up towards the top of the cartoon. If you have a sealed conduit, which I've drawn here with this solid black line around it, the gas really can't go anywhere. So it really needs to expand because pressure is dropping and pressure is being released. So instead what happens is you generate big steam pressures that can break the rock up at the top of the volcano. And when you break that rock, then all of the magma comes rushing out in fragments as the pressure is released and you generate a big violent explosive eruption. On the right, I've drawn a perforated column of magma here. So the conduit is leaky. That means that these gas bubbles that I've drawn here in blue are able to actually leak out the sides of this leaky pipe. So this is like a leaky steam pipe. You can't generate a lot of pressure inside of this pipe because the gas can escape. As soon as it starts to expand, it just percolates out into the into the mountain and relieves the pressure inside the volcano. There still may be enough pressure of these gas bubbles expanding to propel the magma out of the conduit, but it doesn't explode. It just has an effusive eruption instead. So explosive eruptions happen in the conduit of a volcano when you have a few things going on. One, you have a very tightly sealed conduit, like a sealed up steam pipe. Two, you have very high viscosity, stiff magma. It has high SiO2 content. It's probably also cold. That traps the gas bubbles in place. So when they try to expand, they can't really change in volume, so they build big explosive steam pressures. You have lots of gas bubbles, so you have a lot of steam pressure to begin with. The steam and gas pressures can build up, but the gas can't escape easily, so this makes the pressures build to extreme degrees inside of that magma. As soon as the magma has enough pressure to break the rock, sealing up the conduit, you can get an explosive eruption, lots of ash produced, like this picture of Reventador. So this is just sort of a cartoon. The background picture is Mayonne, and we're going to imagine we have a sealed up conduit shown by this cartoon underneath Mayonne volcano. Down deep in the earth, you have magma that's shown by this red blob. It's got some gas bubbles in it, but most of the gas is dissolved in that magma because it's under very high pressure. As soon as the magma starts to rise to the surface, you create new bubbles. Those gas bubbles want to expand, as shown here by the little blue ovals with the arrows in it. As the magma rises, the gas expands, new bubbles form as the pressure drops. The expanding gas can push the magma up to the surface really fast. As soon as you get up towards the top, you get extreme explosive pressure, and the magma rips itself apart in this process called fragmentation. When that happens, you get big gas rock explosion. You get a lot of ash produced because the magma's pulverized itself apart. And you get this situation like Mayonne in the background here during the 1980s. Highly explosive eruption, lots of ash. Okay, so when you have an effusive eruption, things are a little different. In this case, your conduit is fractured and open and leaky. The steam and gas can escape really easily, relieving the explosive overpressure. The magma also may be low viscosity and low SiO2 content, so the bubbles can move around a little bit more easily. There's may also be not very much gas to begin with, so the magma did not start with a lot of steam pressure, explosive dissolved gas in it. Typically, this situation leads to effusive eruptions. There's an exception here, though. High SiO2 content, high viscosity magmas like rhyolite can also erupt effusively. And the key important factor here is they have a lower gas content, so maybe all of their gas was erupted earlier in the eruption, and they have a leaky conduit. So like Novarupta Rhyolite Lava Dome here in Katmai National Park, that was the last phase of a highly explosive eruption from this volcano. And the violent eruption that preceded the lava dome formation probably got rid of a lot of the gas from the magma, as well as fractured up the conduit underneath to allow the rest of the gas from that magma to leak out. So we're going to revisit this cartoon again here and show just a progression of how this might happen underneath a volcano like Mayonne in the Philippines. If you have a leaky conduit and you start off with deep magma that's got a lot of gas in it, bubbles are starting to form. When the magma starts to rise to the surface, as soon as the new gas bubbles form and the pre-existing gas bubbles expand, the gas actually can just escape, leaks out of the conduit and into the volcano just to diffuse away. The result is you get an effusive eruption of a lava flow. You may have enough gas expanding in your magma to propel the magma gently out of the volcano, but there's not enough to create that violent fragmentation process, so the result is a lava flow.